All right, so in section 4.5, we were looking at problems like this. F of t is a piecewise defined function. It's cosine pi t if t is less than or equal to 2, and it's 0 if t is greater than 2. And we wanted to find the Laplace transform of that function. Well, what we had to do in order to find the Laplace transform of that function is we had to write that function using the u notation. So how did we do that? How did we do that when we wanted the function to be something at the beginning and then 0 everywhere after? It's 1 minus u of t minus 2 multiplied by your function, cosine pi t. Okay, so that's going to be cosine pi t minus cosine pi t times u minus 2. Do we know the Laplace transform of cosine pi t?
Yep.
Yes, it's
1 S.
s over
Over
s squared plus pi squared. Correct. Max?
Oh, yeah, no.
So this piece we can be done with. We know the Laplace transform of cosine pi t. The problem is this one. If you have the
Yeah.
that was some sort of new notation there. If you have the u of t minus 2, you need your cosine to be cosine of pi times t minus 2.
It's going to work out to be like negative cosine pi t again.
Yeah, so let's see. So what you kind of do is you kind of come off to the side here and you write down cosine of pi times t minus 2. That's cosine pi t minus 2 pi. And what you need to know is I need to get rid of this cosine pi t, and I need to write cosine of pi times t minus 2. How are these two things related? Can I just slap in a t minus 2 and have it work out? Or do I need to perhaps change a sign? Well, what can you tell me about cosine of pi t minus 2 pi? Make it what? Okay, you can do it that way. That's cosine pi t cosine 2 pi plus sine pi t sine 2 pi. So this one works out really, really nicely because the sine of 2 pi happens to be 0. So that piece all goes away. Cosine of 2 pi happens to be 1. So it turns out this time that cosine pi t is exactly the same as that. So I don't have to fiddle with any minus signs this time.
Great bonus question.
Couldn't you just say that it absorbs it basically because it's going to be the same angle?
That would have been a much easier way to do it. A much easier way to do it would have been to say, you know what, I know that the period of cosine is 2 pi. So subtracting a 2 pi just does a shift by 2 pi, which really doesn't do anything. You're absolutely right. I didn't really need to use that identity. All right, so we can just rewrite this as cosine pi t minus cosine pi of t minus 2, u of t minus 2. We can do a direct substitution this time. There's no issues with minus signs. Those two things are exactly equal. Final answer then. I take the Laplace transform. The Laplace transform of f of t is, we said this one was s over s squared plus pi squared minus, how about this one? What happens when you have the u of t minus a? You get an e to the minus as. So in this case, it's e to the minus 2s times s over s squared plus pi squared. Go ahead, Max.
I'm just kind of confused as to why you have to do that.
Because if I want to use this theorem, if I want to find the Laplace transform of u of t minus a times something, this something has to be in the form of f of t minus a, not just f of t.
Okay.
So I need, if I have t minus 2 here, I have to have t minus 2 there, not just t.
Okay.
It turns out for this problem that cosine of pi t and cosine of pi times t minus 2 happen to be exactly the same thing.
Okay.
So it really doesn't matter for this problem. You get lucky.
Yeah.
Works out perfectly.
Great bonus question.
Great bonus question.
George, when we figured out the cosine pi 2 minus t, what that equals, was when we used the identity that Greg had mentioned, was that a plus between the cosines and sines, or minus because there was a minus inside?
The cosine pattern, if you have a minus here,
Yeah.
you get a plus there.
But the sine stays the same.
Sine stays the same. Yep.
How did we get to that cos of pi times 2 minus 2? I don't
This?
see, yeah, I don't see where.
Once again, what I was doing is I was looking up here and noticing that I had a u of t minus 2. If I have a t minus 2 here, I have to have a t minus 2 there, not just a t.
Oh, okay.
So what I did is I went off to the side and I said, well, I'm going to put in a t minus 2 right there. And I'm going to use my vast knowledge of trigonometry to find out how this is similar to what we have. And it turns out that they are exactly the same. So I can just, instead of writing cosine of pi t, I can write cosine of pi times t minus 2.
That would be the bonus question.
Now, it doesn't work out that they're always exactly the same, of course. And that's what we had last time. Last time we had one that this and this turned out to be opposites. So we had to throw in a negative sign. Questions on that? Okay, the last thing that happens in section 4.5 is the last theorem on Laplace transforms. If f of t is periodic with period p, then the Laplace transform of f of t is 1 over 1 minus e to the negative ps times the integral from 0 to p of e to the minus st times f of t et. Okay, so consider this nice periodic function. So on and so forth. So what you can think of is, think of having our differential equation that involves an electric circuit, and you're turning the switch on for a second, then you're turning the switch off for a second. Then you're turning the switch on, then you're turning it off. Then you're turning it on, then you're turning it off, over and over again. What happens in that circuit? Weird stuff, yeah, probably. On, off, on, off, on, off, on, off. You keep going over and over and over again.
Don't tell people.
Okay, so is that a periodic function?
Yeah.
Yes, what's its period?
P.
And p is a number. P is which number? Not 1. 2. Why 2? Because it's on, then off. That's one cycle. On, then off. That's another cycle. So the period here is 2. P equals 2. So the Laplace transform of this function is 1 over 1 minus e to the minus 2s times the integral of e to the minus st times that function. Now, what can you tell me about that function? Well, that function's either 1 or 0, isn't it? So it's pretty easy to integrate when it's 0, isn't it? When it's 0, you get 0. So I really only need to worry about integrating the part of that function when it's 1. dt. Now normally my bounds would go from 0 to 2, but I only really need to go from 0 to 1. Why do I really only need to go from 0 to 1 instead of 0 to p like the theorem says? Because from 0 to 1 it's 1, from 1 to 2 it's 0, and the integral of 0 is 0. So just because you have a p here in your theorem doesn't mean you're always going to have the number p there. You got to kind of look at your function and decide, hey, for this one I only got to integrate over half of it.
If you put 2 there, would it affect it?
Absolutely. How come?
0, p.
Because eventually I'm going to take the antiderivative and then I'm going to plug these numbers in.
Yeah.
And if I plug in 2, I'm going to get a different answer from when I plug in 1. So absolutely it makes a difference. So you do need to make sure you have the right numbers there. Questions on that? So you would find that antiderivative. What's the antiderivative of e to the minus st?
Negative 1 over s.
So we're going to have 1 over 1 minus e to the negative 2s times negative 1 over s e to the minus st. And then we're going to plug in our numbers. Final answer looks like 1 over 1 minus e to the minus 2s times, when I plug in 1, I have negative 1 over s e to the negative s minus negative 1 over s e to the 0, but e to the 0 is 1. That's it. Questions on that?
No, that'll be a bonus.
Possibly a bonus question from section 4.5.
Yes. I think
The theorem is on the sheet.
so basically,
Everything you need is on that sheet,
it conforms to
except for doing partial fractions. That's prerequisite material that you learned in Calc 2. So it's not on the sheet.
You should have memorized it.
Other questions?